When the sea ice around Antarctica freezes each year, it grows to a thickness of 1 to 2 metres and covers an area of approximately 20 million square kilometres, which is about 1.5 times the size of Australia. Icebergs, which originate from glaciers coming down off the Antarctic plateau, get entrapped in this sea ice as it forms and creates a rather unique and spectacular environment in which to work. I'm Fiona Scott. I'm a marine biologist with the Australian Antarctic Division, and I've been wintering here at Davis Station for the last 15 months, studying the microorganisms in the water column and also those that are incorporated into the sea ice, which surrounds most of Antarctica during the winter. In spring and summer, increased light and temperature causes the microorganisms in the sea ice to bloom. These organisms are an important part of the microbial food web, which forms the base of the classic Antarctic food chain of krill, squid, birds, seals and whales. The non-photosynthesizing species of the community, that is the microheterotrophs, consume bacteria and other unicellular plants and animals, respiring and reparceling carbon as they do so. So in essence, the microbial food web determines the fate of much of the carbon in the oceans and impacts upon the amount of carbon released to or lost from the atmosphere. Well, I'm 6 kilometres from Davis Station, which is over in that direction, and this is one of my sample sites, and it's very possible that might be the last time I sample here, because I know there's a big storm coming in a few days and it may take the sea ice out and these icebergs completely. So I'm now coring through 1.9 metre sea ice, and hopefully when I've finished I'll pick up an algal mat at the very bottom of that core, which contains diatoms and other protists, which are the organisms I'm working on. Hopefully I'll be able to show you this algal mat at the bottom of it. So I've just pulled up the ice core out of that hole that I cored, and this brown layer here contains diatoms and other protists. So what I would do now is take this, cut off the bottom part of this core, take it back to the laboratory and prepare the organisms for scanning electron microscopy. Cells are generally less than 100 microns in length, and many can only be accurately identified by electron microscopy. In preparation for scanning EM, the steps include a sequence of filtration and concentration of cells, attaching the cells to polylysine-coated cover slips, fixation and critical point drying, and finally sputter coating with gold before transporting the material back to Australia. Most of these organisms are unicellular, grouped within many classes of algae, bacteria, motile flagellates and ciliates. During the winter, the standing crop of microplankton and primary productivity of Antarctic waters are low, but there is still an impressive diversity of organisms, possibly numbering hundreds of species. So it's very easy to see that what these organisms lack in size, they make up in number. If we are to understand the processes of global climate change and the impacts of change upon the food available for grazers, then we need to know what the sea ice community is made up of. We also need to know how these communities change seasonally, that is, change in terms of species composition, abundance and trophic function, and how they are affected by their environment, such as increasing temperatures and ultraviolet radiation. So it'll be many, many months before I get back to Australia and can actually look at these organisms under the electron microscope. And for me, being in Antarctica, it's not just the beauty of Antarctica and the icebergs and all the wonderful animals, but it's getting back and seeing Antarctica through a microscope, seeing all the fantastic diversity of organisms that the sea holds for us.